Hello, everyone. Welcome to the tutorial session of healthcare data mining with matrix models. Here, I will introduce the part 2. I just want to do some introduction for myself. My name is Zhang. My background basically is data mining. I have a PhD in data mining, but I have some intern experience. I think it should be 5 years ago. I have an opportunity to go to a pharmaceutical company, GlaxoSmithKline, and I have a summer intern in GSK. And after 3 months of the summer intern experience, manager satisfied with my performance, and they asked me to stay there, basically stay there for 1 year. So I have 1 year and 3 months experience in pharmaceutical company. And I finished my dissertation in pharmaceutical company. And then I come and join IBM. So I have some background in both biomedical informatics now because I have some training in pharmaceutical company. And also I have PhD in data mining machine learning. And also after my joining IBM in 2012, fortunately, I'm working closely with a lot of very smart people, like Jimon, like Fei, as you already see. And we have a lot of collaboration in healthcare and also in biomedicine in this domain. And my talk is basically, a lot of people ask, what's the difference between the session 1 and my session? So in the session 2, I have a little bit different presentation focus. I will introduce the algorithm, and I will put more emphasis on why we should use the algorithm in this problem and why this biological problem is important. So basically, I will focus on the different problem and also introduce the algorithm itself. Today, they have a lot of measurement in biomedicine. For example, everyone knows should use once we have DNA, and DNA transfer to the message RNA and go to the encode as the protein, and this is the whole flow. And during the story, we have a lot of omics technology here. For example, at the genomics, we have the DNA copy-number variation assessment, the mutation sequencing, and also from the DNA to mRNA, they have a lot of measurement, like the gene expression, microRNA expression, and also protein expression, a lot of expression here. In other words, in biomedical domain, they have a lot of data, a lot of measurement here. How to get the data and where get the data? Fortunately, they have free data we call the TCGA, the Cancer Genome Atlas Research Network. And in this network, they have a measurement for 12 cancer. It's 12 cancer tissue and have a lot of omics data like the mutation, the copy number, gene expression, DNA methylation, microRNA, protein expression, and also clinical data. A lot of different tumor tissue and a lot of measurement for the human tissue. Then the question comes, how to do data integration from multiple heterogeneous sources? For example, we have methylation data, right? We also have that gene expression, and also we have clinical data. How to combine different measurements together? I think is a problem. They have a lot of issues. The first issue is they have a large number of measurements, but a relatively small number of size. Usually they have 10,000 different genes, and also a lot of measurement in the demographics. However, usually we only have 1,000 patients, so this is the case. And also, we need to find algorithm to integrate common and complementary information. And also, not all measurement can be normalized and mapped to the same unit. So this is a problem. And it's very hard to combine them together to get a vector and to do the data mining, machine learning algorithm. So it's very hard. How to do this? So the first part of research, I will introduce a paper by Wang. It's the Similarity Network Fusion for Aggregated Data Type on Genomic Scale. The paper is published in Nature Method. The paper is very straightforward. Once we have a lot of genomics data, a lot of measurement from omics technology, we can build networks. The network is not like gene network. The network is the patient similarity network, as Fei introduced in the first session. They can measurement the patient similarity based on the methylation, can measurement the patient similarity based on the gene expression, and also can measure patient similarity based on the demographic information. And the second step in the integrated network using a data fusion method. I will introduce the method in the next slide. Once we have some data, how should we measure the patient similarity network? So once we have a patient and have a mRNA expression, they have gene, right? So the patient and gene are two domains. We can measure the urgency matrix between the patients. So basically, to measure how similar the patient to each other and just measure the distance. So this is the first step. We have a urgency matrix P to measure the patient similarity. And we can also enforce a sparse kernel here. Basically, it's just a very simple k-nearest stable kernel. It's just the measurement. Once we have a fully connected patient similarity network, we can enforce they have the neighborhood should the k nearest neighbor of the given patient. Then we can have a graph here. This is the full observation of the patient similarity matrix, and this is the sparse patient similarity matrix. For example, the patient 1 and the patient 2, since it's not very similar, right? So from the mRNA expression, these two samples is not similar enough, then there are no link here. And for the P2, and for some link like the P9 and the P8, I think these two is very similar, and also is shown in the urgency matrix, and we can think they have some link here. So it's very simple methodology. They have a matrix P and also have a matrix S. Once we have these two matrices, and we have a way to make the raw data into the patient similarity network, and this is the patient similarity network A, and this is the second patient similarity network, right? So so each node is a patient, and the width of the link indicated how similar each patient. So it have two very different patient similarity network here. And regarding to combined similarity network, the methodology is use the data fusion methodology. And the node is the patient, and the patient similarity based on the mRNA is in the blue. And the patient similarity based on the DNA methylation I think is in red. And if the association supported by both data is in the pink. So in this network, we can definitely think like this way. In the second step, we can see some links is still here, right? For example, this link is still here. But some links, they don't have link in the graph 1, but they have some information here in the graph 2. Then we can combine the graph 2's information into the graph 1. And for some information, I think like this one is weak enough, but there are no reference in the second one. So this one is dismissed. So basically, this methodology, they have a way to iterative to upgrade these two networks. And the benefit is, as I mentioned, the strong links is still there. And if both networks have the same strong links and you get strength, these two, for example, these two, they have some very strong link and they still retain the graph. For some link, although it's very, very weak link, but so this one I think is very, very weak link, but they have both information in both graphs. They get retained in the graph. So in this way, so this methodology can be also extended to more than 2 different data types. If they have 3, we can just make this in a loop, and the information propagate from one graph into the second graph to the third graph, etc. And it's in the loop. Then this is the overview of the methodology. We have the similarity network, and we have methodology to make one-round data fusion. And if we, once the algorithm is converged, right, they have a fused similarity network here. Then we can get the fused similarity network. And this is the algorithm by that Nature method paper. So it's pretty straightforward, but it works well. So in the next, I will introduce the case study for this work. The case study is based on the cancer. The cancer is the GBM. The data is come from the TCGA data, and the GBM itself is a very, very malignant cancer. I think if the patient have this cancer, the average survival time is just 14 months, so it's a very bad cancer. So they have a lot of information to encode the patient's similarity network. For example, the people can use the DNA methylation data, and they can create a methylation patient similarity network, and also can use the similar way to encode the mRNA expression and also the microRNA expression. They have a lot of features here. Once we get the patient similarity network, it looks like here. And one authors to use the data fusion algorithm, and they get the fused patient network. It's much clean, right? In other words, they have a lot of dense connection in each cluster. And also, they have very little links between the clusters. And if we take a look at the similarity type, and the green indicate the evidence is all in by microRNA. The blue means the information is all in by the message RNA, and the red means the information is come from DNA methylation, and the yellow means they have 2 different sources from the microRNA and the methylation, and etc. And a little bit black means the link supported by Wolf data type. And each node actually is the survival time of the patient. So it basically is just like clustering problem. And for this study, I think the interesting part of this study, the authors is also study the subtype of these 3 different networks. For example, they find the 3 different subtypes of the GBM, this cancer. And they also analyzed the 3 different subtypes. The red one actually is the survival curve of the subtype 1. The yellow is the subtype 2, and the blue is subtype 3. It's very interesting is for the subtype 3, the patient is younger than the previous one, than the subtype 2 and subtype 3. It's interesting. And I will show you another, this is just the clinical property of subtypes. And if we take a look at the treatment, for the GBM, for this cancer, they have only one drug. the drug called the TMZ, I think is TMZ, right? TMZ, the black curve is just to show if the patient do not take the TMZ, and the red curve to show this patient take the TMZ, and just to compare the black curve and the red curve. If we take a look at the curve, another very interesting observation, right? Although the subtype 1 and subtype 2 is the similar, the age is very similar, but subtype 1 it seems that TMZ is very effective, but the subtype 2 is not very effective, right? So this is two observations. One is the group 3 is very young, and the second one is the different response of the subtype 1 and subtype 2. The authors also take a look at the biological properties of the subtype. For example, for the gene expression, very interesting thing is for all of the patients have the gene mutation IDH1 belong to the subtype 3. So in the literature, it's well known. For the patient with the IDH gene, the survival time should be longer than the other patient, other GBM patient. So this to explain part of the why the clustering or the clustering algorithm works well and is correctly to identify the subtype 3 which have a very good survival time. And once we take a look at to another genes, couple of genes, we can find to compare the subtype 1 and subtype 2 patients. And they have a gene overexpressed, the CTSD gene overexpressed. So compare the subtype 1 and subtype 2, the CTSD gene is very popular in the subtype 2. And this explains why the TMZ is only working in the subtype 1 and not subtype 2. They conduct some follow-up analysis. Is discovered the CTSD gene block some TMZ's biological signaling pathway and cause the TMZ drug doesn't work for the subtype 1, subtype 2, but it works well in the subtype 1. So this is another story they show here. The author also go further than this. They also show the network-based methodology can also have some beneficial on the subtype-based, have some network-based outcome prediction. So once we have a patient have the GM to diagnosis as a GMB. So for example, a new patient come, and we have a lot of training patient cohort and how to predict how long the patient will survive. So in the state-wise analytics, is usually just like a grouping, and we can use some classify to make the decision. The patient belong to the subtype 1 or subtype 2 or subtype 3, right? And for each patient group, they have some survival curve like 1, 2, 3. And once we assign the label to the new patient, we can use the survival curve to make the prediction. Use the Cox regression to make the survival time for subtype 1 patient. That's it. For the feature analytics, the author suggests it's not very efficient. Basically, we can do some prediction, use the whole graphs information to do some network regression to make the prediction how long the patient will survive. The idea is pretty straightforward. If we take a look at the Cox regression's objective function, it's just like this. The authors just like they have a network regressor objective. They incorporate the fused patient network structure here, and the patient network is identified by their algorithm, by their data fusion algorithm, and they add the network structure as a constraint here. And in their experiments, they have a discovery data site to build the patient network, and also they have a validation data set to test whether their algorithm is accurate enough or not, and they do some comparison. So for the baseline, they use the PALM15 and the iCluster, these two algorithms. These two is a very famous survival analytics algorithm, and they make some prediction. And also, they use their SNF algorithm to cluster the patient, like 5 cluster and 10 cluster, to show the CI index is very similar. It's not very higher than the state-of-the-art. And if they compare the state-of-the-art with their network-based Cox regression, the CI index, basically to compare the risk, the predictive risk with the observation in the data, the CI index is higher than the clustering-based methodology. And they have a summary here, like use the network-based, even they don't have ground truth. They don't have any ground truth for the patient subtyping because it's a data-driven thing. They don't have any label to assign the patient to each graph. They just do some analyze and incorporate the network they identify from data. The CI index is higher than the clustering-based methodology. So this is the first part of the case study. In this case study, we introduced the methodology is by Wang, is the Similarity network fusion methodology, and it creates a unified view of patient based on multiple heterogeneous sources, and it can integrate gene and no-gene based data, and it's very robust to different type of noise because they have very simple. It's just the k-nearest neighbor kernel, and to make the noise disappear basically. And they have some good result in subtyping and outcome prediction, and they claim the algorithm is scalable. In other words, they can integrate many different sources and into the network and to do some optimization. And for me, I think for our big data researcher, I think for this methodology, I think it's not very fancy. It's just like the kernel thing and the data fusion thing, but it's published in Nature Method. So the lesson I learned is we should study hard and to make a lot of comprehensive story, right? They have a comprehensive story to find the subtype. They do the clinical cohort analytics. They do the gene expression. They do gene analytics. Also, they do the survival analytics, right? They make the story very comprehensive. Then they publish in Nature Method. Is the infect factor, I think, is the 14 or so. So it's great. Okay, so in the first case study, I just should show once we have a lot of information for one domain, which is the patient domain, how we can use the matrix model to make the prediction or make the subtyping, right? So the second part, I will introduce our work on the geographic positioning, and I will introduce a joint matrix factorization methodology here. Hi. They have, so in this data, they have, you mean how many different domains they have, right? So in this case study, they only, in the experiment, they only have 3 different domains, like the gene expression and the methylation, and also I think they have, sorry, I forgot the second one. Yeah, they have these 3, just have these 3 domains. But the algorithm itself is very flexible, as I introduced in my very first page. In the TCGA, they have a lot of different omics techniques, right, to measurement each patient. Basically, it's a patient with a lot of vector value, right? So basically, we can build the patient similarity network on all of the information. And we can add all of the different information to measurement the patient similarity network and merge into this framework and got solved.
So did they mention anything that, for example, as the domains increase, the knowledge is watering down, more sparse information?
Oh, so you have a very good question. So you mean maybe maybe we integrate some noisy data sources and the performance is going down, right? So it's a very good question. And they do try some experiment because in this algorithm, they do for the noisy. Okay, sorry, So the algorithm itself is to make the strong link is strong and make the weak link, like the noise, disappear. It's basically like this way. And for some weak link, as I mentioned, for some weak link, because they appeared in many different sources, so it's a reliable link. They think it's a reliable link and it's retained in the partial network. So
I'm just wondering, for here, you basically combine sort of like similarity network, right?
yes.
So for the similarity function, you can choose different one, and for the combined step, maybe you can do this like recursive update, or you can just take the average. So is there any difference between like different strategies?
You mean the strategy to use this way to combine different resources? Your question is about how to choose the methodology to construct the patient similarity network?
Like two questions here. One is for the similarity function.
Yes.
You can definitely use different similarity functions.
Yes.
For the combined step, I think you can also like maybe not this combination one. Maybe you can use different one.
Yes.
Any like comparison for different work, but compared with this.
So the question is really good. So for the second question first, second question is how to compare this methodology with different state-of-the-art methodology, right? So in the paper, the author do to compare different methodology. And for example, in the Cox regression part, they compare different state-of-the-art. So it's a different methodology for the same problem, data fusion problem. And you ask a very good question in the question 1, is how to construct the patient similarity network. So unfortunately, right now, they don't have a golden standard for each data sources. For example, for the gene expression, people usually use the cosine to measurement the similarity, and some other people use another methodology. If there are some binary, people use the Tanimoto coefficient. If they use some continuous variable, people usually use the cosine function. But you can try. You can try which one is good, and you can encode this information in the matrix model. Hi, please.
Do you know whether they use the clinical trial data for this particular drug?
For what? For which data?
Whether they use the data from the clinical trial for this particular drug?
They use the TCGA data. So they use the TCGA, which have a lot of measurement for this cancer patient.
So they did show, I don't think that there was a lot of noise in the data.
Oh. Okay. Okay. Good. Thank you so much for your comment. Okay. For the second part, I will introduce the joint matrix factorization methodology and the drug repositioning as a case study. For the drug discovery, which is a very challenging task, and right now they have very standard way to design drug. Basically, the scientists to find the disease and to understand the disease, and then find the disease targets, and then design a chemistry to target this drug target. And then they do a lot of in vitro or in vivo animal experiments, and then they go to the clinical trial, phase 1, 2, 3, a long story. And then once they submit it to FDA and do the phase 4 study, and this will cost more than 10 years. And I think it's outdated. I think to develop a new drug is more than $2 billion US. I think it's maybe correct. In other words, drug discovery is high cost, long time, and no successful rate. As Fei mentioned, they have a type of research they call the drug repositioning. Some people call it the retasking or repurposing. A lot of paper about this. It's to application the new drug and the compound to the new indication. A standard use case is Viagra. So the benefit of the drug repositioning is the repositioned drug has already passed a significant number of the toxicity and a lot of animal tests. So its safety is already known, and it's good, and it will reduce a lot of time and save a lot of money. Due to the time constraint, I already introduced the benefit of drug repositioning. Once the people make the prediction, the drug can be used to other disease, and they can just to identify the compound and get the compound and go to the development. Maybe they can start from the phase 2 and also to register to the FDA, and this will save a lot of money. They have a lot of ways to measurement the drug similarity, as Fei introduced before. Like each drug has a chemical structure information. The drug also have the protein target. And from drug label, we know some existing market drug has some side effect keyword. And for the disease part, they have a lot of methodology to measurement the disease similarity. Like from EHR, we have a lot of phenotype and symptom from each EHR. And also from autology, they have a disease autology, and also we know some disease gene. Then what we need to do is calculate the drug and disease similarity. So at this point, I know someone should ask a question, why we use the similarity way to do this, right? Why we don't just run a logistic regression to make the prediction whether the drug can treat some disease? Actually, this is a good question. The reason is we have a lot of disease here. And if we want to incorporate the association between the disease, then it's a very hard multitask learning methodology, and it's very hard to finish. And I will introduce some comparison, and also I just want to tell you the similarity-based methodology is a very efficient way. And here, what I introduce is our paper about the joint matrix factorization. And we have two domains. The first part of the domain is the drug domain. So each D1, D2, D3 actually is the 3 different drug network. And in the network, and each dot actually is a drug. And the link between the drug actually is the drug similarity, right? So the similarity between the drug 1 and drug 2, sorry. And also, for example, this D1 can be the drug similarity network based on the drug chemical structure, and the D2 can be the drug similarity network based on drug targets, and D3 can be based on the drug label or side effect, etc. And similarly, we have a lot of disease similarity network, and each dot actually is a disease, and each link between the disease is the disease similarity. And S1 to measurement the disease similarity based on like gene, disease gene, like the phenotype of disease, like the like the disease autology, etc. And the problem actually is very hard. What we want to we have a lot of disease and drug network, and also we have a little bit label. The label means the drugs existing indication for the disease. It's just a very sparse association between drug and disease. So which is the binary matrix encoded in the matrix R. What we want to learn is the densified version of the R in the theta. It's the first parameter we want to learn. And also it's maybe also very interesting to learn which data resources is more important than the other one. We have a weight. For the weight, W1 is the weight for the drug chemical structure, W2 is for the target, and W3 is for the side effects keyword, etc. And likewise for the pi1 to pi3. And we want to have integrate the drug similarity network and also integrate the disease similarity network. And the framework is very flexible, and we would like to add more drug similarity network together. Here is just the algorithm flowchart. We have an input like a lot of similarity network for the drug, a lot of similarity network for the disease, and we have a hand of drug and disease association, and we want to develop an algorithm, and we can find additional drug disease association, and also which data sources is more important, and also we can get some byproduct like the drug group and disease group. To solve the problem is just like an optimization problem, and it's straightforward, and Face have a lot of experience of this actually, and in his part of the presentation. And we analyze the disease and drug network like this object. The J0 is reconstruction loss of the observed drug and disease association. The theta is the densified version of the drug disease association. U is the drug group, V is the disease group, and lambda actually is to enforce the similar drug and a similar disease have the similar drug and a similar disease group have some similar behavior, because U is the drug group and V is the disease group. And for the J1 and J2 actually is the reconstruction loss of the network. Since the UU transpose is the integrated drug similarity network, and the D1 to D3, because I use the decay right here, to measurement how far the different drug network from the integrated drug network. And also we have some equalizer, and the same thing for the disease similarity network. We use the VV transpose as the integrated disease network, and the S1 to S3 or KS as the disease similarity network. And we have two parts of the loss function is encode the drug and disease network. And we put everything together, and we enforce the non-negative, and also we enforce the weight added into the 1, and also we enforce the R. In other words, the observed link should include in the densified version of the theta, so we can solve the algorithm. So this algorithm is the BCD strategy. I think I will skip. So it's straightforward. It's just it's a loop, and we solve the parameter. We have 1, 2, 3, 4, 5. We have 5 parameters, and we solve one by one, and we can finish this. And we have some computation, complexity, analytics. And this is algorithm part. And at the experiment, and we do some analytics. We have 799 drugs and 719 diseases. And we have, as I mentioned, we have 3 drug similarity networks from 3 different perspectives. And we also have 3 different disease networks from this number of the disease similarity network. And it's just to show some distribution. Some drug actually is the popular drug, and some disease is the popular disease. Like aspirin treated a lot of disease, and hypertension have a lot of drug to treat. So it's just to show some statistics thing. And at the end of the comparison, and we compare a lot of methodology. If we use our methodology to do the weighted drug and disease similarity, and we have a very high AUC. And if we just use the simply average, because we have a lot of similarity network, if we just use the average of the 3 different networks and use some state-based methodology, and it's not good enough. And also we do some comparison of the disease and drug, and also some logistic regression-based methodology. I think it's not logistic, it's the kernel learning methodology. And one byproduct of this methodology is can compare which data sources can contribute more than the other resources. So this is an interesting part of the study. At the end of the day, we find the set effect disease phenotype and disease autology have more weight than the chemical structure, target, and disease gene. So this is our paper, but some pharmaceutical companies don't like this because they are biological people. They think the chemistries think the chemical structure is good, and the biologists think the target protein is good. So, but I have some explanation is about the translational factor, because in the drug discovery, although the scientists design a drug and the drug can pass the animal can go to the in vitro and in vivo experiment. I think only 20% can pass the animal model. So even it works in the in vitro, in the tube in the in vitro, only 20% can works in the in vivo environment. In other words, in the mouse or the dog experiment. And once apply the drug, given drug to the human beings, I think only 5% can work at the human beings. In other words, they have a translational gap to transfer from the lab test to transfer from the laboratory results into the animal model and into the human model. So they have a translational gap. And our discussion like the cell effect, which is the directly observation from human beings, and disease phenotype is from EHR, and disease ontology is the literature many. So these three things basically is direct observation from human beings, and it works well. So it's my partial explanation. Maybe good, maybe wrong. I don't know. So how to use the algorithm to do the drug repositioning? Since what we want to do is to do the drug repositioning, we really want to predict which drug can treat some disease. So in the result part, we use the leave one disease out algorithm. We just think there are no treatment for one disease, like the Alzheimer's disease. And we make a prediction, and it's the ranked list in our prediction, and from higher to lower. We find interesting is our algorithm can correctly to retrieve some well-known treatment for the AD, like the VA and this drug and Silagilin. And these three drugs actually is the known drug to treat AD. So we correctly to retrieve the known drug for the Alzheimer's disease. And also they have some drug like the metformin and bexarotene for these and also levodopa for these three drugs. Although they are not known drug for the Alzheimer's disease, but in the clinical trial, we find some evidence to show these three drugs are used by the pharmaceutical company to treat the AD patient. So in other words, our algorithm can retrieve some information from the clinical trial. And for all of the other prediction, like these four drugs, which is not appear in the literature or in the clinical trial, it can be variable repositioning candidate, and we can send this candidate to the pharmaceutical company, basically. And for the summary, and this paper is published in 2004 EMEA, and you can take a look at. And we proposed, in general, computational framework to do the drug repositioning task. And this framework basically is very flexible, since it just have two domains and have a lot of resources in each domain, right? So we can apply the methodology to a lot of similar problem, right? Like the gene disease, if we have a gene, a lot of gene information, a lot of disease information, we can directly apply this algorithm. If we have the drug information and the patient information, we can also apply this algorithm to the drug and patient network. So at this point, someone, I think when I presented this to the people, someone will ask, whether is there any company use this algorithm to find some new drug? I think it's a good question. And in this presentation, I just explain my work in IBM. So we have a group, it's the Translational Informatics group. And what we want to do is the multi-channel detailed computational hypothesis generation. In other words, we are the computer scientists. We make the prediction whether the drug can be used to treat disease. And the pharmaceutical company, or if we want to sell something to any client, we need more evidence. We need more evidence and to do the detailed hypothesis generation. For example, I make the drug can treat the Alzheimer's disease. I need to make the prediction from different perspectives. For example, we should analyze the structure of the drug, the bioassay, the gene expression, and the genomics data, and also the real-world evidence. We have some real-world data to show whether the drug can treat some disease. And we do the multi-channel hypothesis generation, and for each drug, we have multiple evidence to show this drug can treat the disease. And the pharmaceutical company can use our result to invest it and go to the animal model, to go to the clinical trial, and find a new drug for the patient. Basically, is our goal. And sometimes we can even do beyond the hypothesis generation. So this is the scientist, I think the website is the scientist.com. I forgot the exact name. They have some animal model. It can be purchased just like Amazon. For example, if we make a prediction like the drug can treat some diabetes patient, right? So they can help us to build a mouse model. And for example, the description is this is a China company that helped to do this. They raise the 16 mice, and also they do a lot of in vitro and in vitro experiment. And how much this is cost? Any number? How much this experiment cost? So it's not very expensive. So it's just $9,000 US. To validate this prediction, it's just $9,000, and it's what only take 9 weeks. And I just deleted the information of this company, and some people say for this evaluation it just cost $2,000 for 4 weeks. I would not ask a postdoc to spend a year to set up this in the lab, just like this. So my point is, right now we have a lot of CROs, and we can just send this part of work to the outside partner, and big data researcher right now have a higher impact in the biomedicine now. So this is my so I think it's my research experience is because I work a lot in the pharmaceutical company project, and sometimes we make a lot of good prediction. And once we want to make the prediction to make more impact, in other words, to go to the animal test and also make this prediction to the clinical trial, it will take a long, long time. We need to find a collaborator. We need to find some hospital, and but right now they have the crowdsourcing website basically, and we can do this simply. And you can search in the website a lot of the CRO companies here. So it's a good time. Use the big data to influence the biomedicine industry, basically. So any question about this part, geographic positioning? Please.
So your assumption is that similar drugs can treat similar diseases?
Yes.
So with this model, can you reposition the other? Because it's basically for hypertension. So can you find completely treatment for different diseases?
Very good question. Basically, how to define the similar drugs is not that easy, because originally people just use the chemical structure similarity, right? They only think that the drug have some very similar chemical structure. They belong to the same drug group, and then it's the same drug. It's a similar drug and treat some similar disease. But in this framework, actually, we consider more than just the structural similarity. We also consider the biological network, and also we consider some phenotype information. For example, some very different drugs have very similar side effect keyword. Then we think these two drugs also somewhat similar. The drug can be in very different therapeutic group, but they have some data. They have some data to say these two drugs similar. Then it's also be considered in our prediction, right? So please continue.
Have you considered just to mine like a medical claim database? Maybe some person they just take hypertension drug, suddenly the drug help them to cure their asthma or maybe other disease. Have you tried that?
You mean use the hypertension drug to treat the asthma?
I mean just mine the electronic health record.
Yes. So.
Some people taking drug for one disease, but data shows at the same time may have help with other diseases.
Exactly. So this is another direction of the research is like the causal inference to show whether the drug have some accidental effect for some disease. So it's just to show whether this signal is causality links, right? So for this part, we also have additional work for this. It's a causal inference work. So it's nothing about this. For this prediction, we just at the prediction stage. We make the prediction, the drug, from a lot of drug data, from a lot of disease data, we can make the prediction, right? So once we make this prediction, we will search the EMR, to search the claims, and to find whether they have some causality links here, and to make the prediction. So it's a different channel.
Have you had any pharmaceutical companies that validated your prediction?
So in which way? In vitro, in vivo? Right now, we do make some prediction, and some collaborator is validate. And for example, in my intern work, we identify some drug, right? And GSK have some clinical trial in our prediction. So it works. So in the preclinical prediction, sometimes works, but it sometimes takes a long time. So that's why I add this part of work. The big data researcher can also have some choice to validate their prediction. Thank you.
Okay, so basically for your drug and disease, you basically got data groups, right?
Yes.
So how do you determine the number of them? Based on domain knowledge or just by experiment?
It's just by experiments. In the study, I think for the drug group, we have 20, and disease group, we have 10. So this is in our experiment, but I think we can set up more than this number. Question, please?
I noticed that for some disease or for some drug has multiple or extra more entity link in the database. So do you think it gives the drug or disease higher chance to link to other disease or drug?
Yeah, definitely, I think so, because we consider so all of the existing drug and disease association we encode in the matrix R, right? So it can be similar like face label, right? So for this part, we have more dense observation, and we do consider this information to the whole network. And we think it will help to make the prediction. Definitely, yes. So in the experiments, basically we don't consider the quality. What we have extract is from the NDF-RT, which is the drug, basically is the drug label database. We know the drug treated the disease. Like we know aspirin is treated the fever, treated the pain. So just this level of the indication, right?
So it's kind of like a basic quality level because you know it's trade, how it trades, like how effective it is.
So it's our enable data. So it's a drug label data. There are no say how effective you treat the patient or not. Thank you. Okay, so right now we go to finish the second part. the third part I want to, so the first one, as I mentioned, is they have just one domain and a lot of resources, right? And the second one is we have two domains and a lot of resources about these two domains as well. And the third part I want to introduce is the data fusion by simultaneous matrix tree factorization and Dudley prediction. As Fei introduced, they have a matrix factorization algorithm. One of them is the matrix tree factorization. In other words, once we have a matrix, we can do factorization into 3. It's not 2 now. It's not like the NMF is to factorize to 3 different matrices. Like one is the recipe of A, and the backbone, and also recipe of B. And for the matrix tree factorization is just factorize the matrix AB into 3 links here. And I think this part of work is in KDD 2006, and also Fei have one paper on this. And right now, more and more paper is about the matrix tree factorization, and sometimes they show some common information here. For example, they have two links, the AB and AE, and they have 2 links can factorize to the recipe matrix of E, recipe matrix of A, and the recipe matrix of B, and also they have backbone matrix AE and AB. And in the matrix tree factorization, they do just like this. So in the factorization, they show the recipe of A here, right? So A is shown by 2 tasks. So they have a different backbone matrix AE and AB. They have a different matrix because this is, I think, is this B, and this one is the backbone of E, right? But for the part of A, they show it together. So in this work, I think Marinka and Blas published a paper in PAMI last year. They call this is a data fusion, but simultaneous matrix tree factorization. Basically, they have a lot of data, a lot of objective, a lot of domain. So epsilon 1 to epsilon 5 is the 5 domain. And also they have a lot of links here. Like the 1, 2, they have a relation matrix. And 1, 4, they have a relation. And also 1, 5, they have some relation, etc. Also, in the same domain, they also have links. Like the member of the epsilon 2, they have some similarity-based thing. And also they have some epsilon 4, they also have multiple resources to encode this objective, right? So what they propose is the simultaneous constraint decomposition. For example, they have 5 different domains, then they have 5 different recipes, and for each link, they decompose it into the backbone matrix, basically. And to solve the problem, they just extend the matrix tree factorization thing. And to solve this problem, basically they fix G and update S, fix S, update G. So this is the very comprehensive thing. So I will maybe right now is not very clear, and I will use a case study to show the whole idea of this study. So right now is the liver and the Dudley prediction. The liver is a very important organ in our body, which is the chemical engineering headquarters of our body, and is take the internal chemistry, like the hormone, like the blood, and is control everything. And also, liver also take into the consideration a lot of environment chemistry here, like alcohol, environment chemical, the disease, and also the foods and nutritions, and the most important thing, definitely drug. And like the Tylenol people think is the pretty safe drug, but in In the drug label, it says it can cause the liver damage, and if the patient takes its overdose. And FDA think the approved drug as the most common cause of the acute liver failure in the USA. And Dudley is the most frequent reason for the drug to withdraw from the market. In the 2012, for the calm-down prediction task, they have a task is use the TGP data, which is the gene expression database, to predict the daily potential of the drugs. And in this database, they have 113 chemicals, and they have some label to say the very severe, medium, and also mild daily potential. So the database they use is pretty straightforward. They have a lot of gene expression. They have 3 types of the rat and mouse gene expression, basically. They have the mouse gene to measurement, and also they have a lot of mouse, and they have the in vitro, and the single dose in vitro. And for the in vivo, is the single dose in vivo and the repeated dose in vivo. By the way, for the in vitro, is basically to take out of the mouse tissue, then use the drug to treat the mouse tissue, then do the gene expression. So what we call here is the in vitro. And for the in vivo is to feed the mouse at the single dose, and then to take off some tissue from the mouse and to do the gene expression. And the in vivo repeated is basically to give the mouse some drug at day 1, and also at day 2 give another dosage of the drug, and day 3 give another dosage of the mouse to the drug, and after maybe 7 days or 10 days, and then take the tissue out of the mouse body and do the gene expression. So this is different from the in vitro and in vivo. It's just some background knowledge. And also, they also have some humans information. They have the human tissue, but for human, I think it can only do the in vitro, right? So it's not good to do the in vivo for human beings. So it's a single dosage in vitro data. So they have basically four different types of gene expression data. And also, they have the sample metadata, like the dose level, the dosage, and also the period, the animal or human age, and the sex type, the test type, and the species, so like mouse and human. So they have data here. And in the context, people propose a lot of very good algorithm, and the winning algorithm basically is the multi-classified system. And first, they do the feature selection, use the PCA or CUR matrix factorization. And also, they do the stack, use the logistic regression. And they consider random forest, gradient boosting, logistic regression, and SVM. And then after they get the results, use the logistic regression to stack with the result and do the prediction. And the result is pretty interesting. It's basically the rat in vitro have a similar, maybe if not better, it's just a similar performance like the human in vitro. Is in other words, in the in vitro experiment, human in vitro don't have many advantages for the rat in vitro. And how to incorporate the data fusion algorithm to this case study. And Marinka in the case study, they consider a lot of side information here, like in the data. Besides the gene expression and the metadata, they also consider a lot of historical and clinical chemistry data, like the liver weight, blood chemistry, and hematology data here. And also, they also consider a lot of drug information from drug bank. It's chemical structure, like the drug interaction and drug target, and to measurement the drug similarity, basically. And for the protein similarity, because gene can transcribe to the protein, and they also consider the protein-protein interaction from string. And also for the gene similarity, they also consider the goal from gene expression, right? Yes. And they made a very big matrix factorization. Right now, they have 14 different domain now. For example, the first domain is the gene from rate in vivo, and number 2 is the gene from rate in vivo repeated dose, and gene from rate and gene from human, right? So this is first, the 4 domain is the gene expression data. Then they have some sample data from rate in vivo single dose study, and also they have a lot of biochemistry, sample amount data, and drug type, and drug data, daily potential prediction, and gene autology data, and a lot of drug data. And if we take a look at it, they have a lot of link here, right? Each R is a relationship, and a lot of relationship can also carry some data here. And besides that, they also have some constraint here. Like because gene have a gene autology and also PPI data, protein-protein interacting data to measurement the gene similarity. So in some domain, they also have some constraint here. So for the prediction task, they want to predict whether the drug can cause the deadly or not. And they put things together, and they have a much better result than just use the gene expression information and also metadata information to make the prediction. So what we read about is if we consider everything here, and the AUC can reach the 0.8, because previously slide is just the 0.35, right? And if we consider the animal study with the human study, because the human study just have some in vitro data, but the animal study have some in vivo data. So animal study is slightly better than the human study, right? And also they compare the in vivo study, in vitro study, human in vitro, and animal in vitro, etc. So the conclusion is the animal study may be replaced with the in vitro assay, and liver injury in human can be predicted from animal data. And also my conclusion is animal in vivo is better than animal in vitro and similar to human in vitro. And they win some prize in the Canada conference. So in this study, basically they built a large matrix and put all of the domain together and do the matrix factorization. Do you have any question on this?
Yeah, so they are basically doing this joint matrix factorization to fuse different signals.
Yes.
I was wondering if they have uniform weights for different laws from different matrix, or they have different weights.
So this is also I read the paper carefully. They claims this algorithm don't need a lot of pre-processing. In other words, they can put all of the raw data together in the matrix. Basically, this matrix is most important one. They claims they can matrix factorization of everything, basically.
Okay, and they have uniform weights. I was wondering whether the size of the matrix may differ from if you have like in total 40 different matrices, are they on the same scale or?
What does the scale mean? For example, in their case study, the domain can be gene, right? The domain can be drug. The domain. So maybe you mean whether they are scalable?
Number of drugs.
Yes.
Number of genes, will they differ a lot, or actually they are about the same?
I think involved their experiment is in similar scale. Is in similar scale. Similar scale is not 10 times larger than the other objective. But they in the paper they claims they don't use a lot of pre-processing. They don't have any limitation. But I believe since it's used the optimization, they should choose a lot of parameters and tone a lot of parameters and make the prediction works, right? So it's just my understanding. They should tone the parameters, but in the experiment, they don't speak out whether they normalize the matrix, whether they have some necessary thing to make sure the comparable of these different paths. So this is just my understanding.
Another question is, they assume that for each domain, you may have one similarity matrix. But
Exactly like this. Yeah.
So one matrix could be like multiple matrix.
Yes.
Or same specific domain. So can their method incorporate that?
Yes, of course. So they claims they can consider the constraint here. They can constrain all of the similarity metrics in the same domain, and also the relationship between the different domains. So this is the picture to show the idea. So for some, domain, they only have one similarity matrix. Some they have different.
And the other thing is, did they learn some weights on different similarities?
No, they don't assign any weight. They just put things together and solve the metric and factorize this. So I don't think in the formula, I don't think they have some way. Yeah, definitely.
Because different similarity may have different performance now.
Yes, I agree. Yes, I agree. But in their objective function, I don't think they have this capability to do this. So you can try our joint metric factorization thing. We do consider the different weight. So for this part, I just want to introduce the work. If we have multiple different domains, they also have a way to do metric factorization. Okay, I think I finished the matrix type of the presentation, but let's go to a little bit different topic, is the tensor factorization now. The reason I added the tensor here is tensor can be a different type of matrix, and we can consider this in our presentation. So in the case study, I want to show the phenotyping now. If we take a look at the recent KDD, ICDM, and SDM paper, they have published a lot of papers about the phenotyping. What does the phenotyping mean? It's basically the observed physical or biological characteristics of the things is the phenotype, is the observable. And why people do the phenotyping from the electronic medical record? Because in the electronic medical record, what we can see is just a lot of lab tests, a lot of diagnosis code, a lot of procedure. But if we put this into the vector, like Fei showed in the part 1 of the presentation, it can be very sparse, and no one understands what does this mean, right? So my understanding is the phenotyping is important because EMR data is the noisy, incompleted, and inaccurate. So we need to represent the EMR to a meaningful medical concept. And also, for the medical purpose, for some medical paper, they need to extracting the clinical meaningful group of patients from EMR. For example, in the first section, Fei used a lot of CHF prediction, diabetes prediction, right? So for the EMR data, we need to identify a group of patients and do some cohort generation. And this is just the example of a phenotype from a KDD paper from Jimon's group. Although I think the blue is the diagnosis code and the red is the procedure. Although the blue and the red don't speak out, this is a diabetes patient cohort, but it's about diabetes. And for the blue and the red headset, I don't think they don't speak out is the heart failure, but it's the heart failure phenotype. So this is the objective. The most straightforward way is to put the EMR data like the matrix. And for a patient, they have a lot of procedure and the diagnosis, and just count how many patients have the procedure A, procedure B, etc. And sometimes we can make the tensor very straightforward to represent the electronic medical record data, which can capture the structured source interaction. The idea is just we use the sliding window just to test whether the diagnosis or the lab test have some co-occurrence with the drug, and if yes, then we make it as the element of the tensor and make into the binary tensor representation So this is the tensor, how to construct tensor from electronic medical record data. And in the KDD14, and Jimon and the collaborator make the CP factorization for EMR. Once they have a tensor, they do the CP type of factorization. And to make the CP tensor factorization is to make multiple different mode 1 tensors, right? Like and also they have a weight for each different mode 1 tensor. It's just like this. And the procedure and diagnosis and all patients in the same group, in the same phenotype, in the same group basically is the phenotype 1 and etc. to phenotype R. And for some tensor, they have some bells, like in general diagnosis, like aspirin is in general medication. They don't have medical meaning. They put it into the bells here. And in 2015, the same group also published a paper to upgrade their algorithm. They just align with the medical knowledge here and make the prediction, make the factorization scalable, and also do some missing value imputation, and to make the tensor as the full tensor. And so for this part of research is the CP factorization from EMR. And back to my objective, how to use the tensor in the real-world application is once have a tensor and they do the factorization. And once the new patient comes, they have a phenotype projection and to assign the phenotype membership. For example, the patient is the heart failure patient or a diabetes patient or some other type of disease patient. We can make this as a feedback to the physician. And the physician can, based on the algorithm's recommendation, to suggest the efficient treatment for the patient back. So this is how to use the tensor in the clinical practice. And since I have introduced the CP factorization, a very natural question is, can we use the Tucker factorization as well? Yes, the answer is yes. In the last year, they have a JAMIA paper is to use the Tucker factorization for the pathology report. They have a lot of lipoma patients in the free text, and they construct the tensor like this. The one mode is the patient. The second is the atomic, the features like is just some word. And also they have the high order features like the language graph, like these three words usually appear together, like they have some group of words appear together. They just do the Tucker factorization as the one group is P by P group, which is the patient group, and the W by W group, which is, I think, is the high order feature, is the language, is a part of is the autumn group, and this one, I think, S by S group is the subgraph, language subgraph group. And they claims use their algorithm, they can identify some type of cancers from the pathology report. For example, the subgroup 1 is about the CD13, which is lab test, I think. And also they have some symptom, Reed-Sternberg appearance. And the subgroup 1, they think is the Hodgkin lymphoma. And for subgroup 2, because they have large cells and CD10 and the Ki-67, they think is the diffusing large B-cell lymphoma. So these keywords, right? So they use the NLP techniques to mining the high order features from the pathology report. It's just the NLP to find some frequency appeared part of the sentence, basically. So they use both the keyword and also part of sentence, and to compare the result by only use this, and also to compare the result by only use the part of language, just like this. And here is just a comparison about the different strategy to tensor modeling and factorization. I think for the CP one, the CP is pretty flexible and also is easy to explain, right? Because CP to factorize the tensor into one mode phenotype or one mode tensor, and each one and each mode tensor actually is one of the subgroup of the patient, so it's very easy to explain. And for the Tucker, I don't think it's very easy to explain, but the benefit is pretty easy to set up the group, because for the tensor, they factorize the tensor into different model 1 tensor. Then at each dimension, they should have same number of the group, right? So they will have 10 different group of interventions and 10 different group of patients and 10 different biomarkers, etc. But for a tensor, we can assign like, I want to factorize the 3 patient group and 4 intervention group and the G different group, so it's flexible to assign the different group of each domain. So for these two methodology, I think both methodology have their benefit. So Fei and Luoyuan has some paper about this to discuss when to use which methodology. Okay, any question about the tensor? I think in phase point is in his case study is different. In his case study, they have an evaluation matrix, right? They want to identify how to define a patient cohort, when to start, when to start and when to end. They want to make the matrix, right? But in this case study, I don't think they have many different ways to. They are very. Once we have a matrix, I still think is pretty straightforward, because in the EMR they have different type of the methodology, different type of the measurement, like the procedure, like the diagnosis, right? And also they have a time point to associate with this. So we can use a time window to assign this to the tensor, basically to the tensor. I think if the data can be, once the problem is here, if the problem is just to do the risk prediction and the cohort is defined as a matrix, and we can easily to transfer to the tensor. But in his example, I think what he mentioned is about the evolution, how to find a group of patients to the evolution. I think it's a little bit different. It's not the risk prediction. So it's just my understanding. Okay. Thank you for your question. Okay, and at the end of the talk, I just want to use about 10 minutes to show the challenge and opportunity of the matrix model in the biomedicine domain. The first part of the things I want to introduce is, as we see, we have a lot of very good methodology to make either the matrix factorization or label propagation and a lot of methodology Fei introduced before. And right now, in the biomedical domain, they have a lot of data, and each data actually to bring each matrix and each network, like exposome and EP and microbiome and metabolism, protein, transcriptor, genomics data, image data, biosense data, social graph data, a lot of data. And a lot of data bring a lot of network. And a lot of network will provide a lot of challenge to the computer science domain. I think they have more and more data to measurement like patient similarity, drug similarity, and it's a multi-scale network, and different networks have different scale. And how to combine the metrics together will be a problem. So this is the first challenge is for the multi-scale network, how to combine. The second challenge I want to put here is it will be also a dynamic network. It's not the static dynamic. For human beings, from the very beginning, like father and mother plan a baby, right? They have some data generate. And from the newborn person, they have some information here. And when the people get to 10, go to the school, they may have some disease, and they may have activity, and also maybe sometimes they develop some disease, and also even when people die, I think then their information can also contribute to their child, right? So they can do some autopsy and contribute their gene, contribute their information to their child. And also, right now they have some study about this. For example, one of the paper is about the birth months actually affect the lifetime disease risk. They just analyzed the EMR data and a lot of other data to find some disease only appeared for the people born in some months. I think in February, the disease, like the diabetes, I don't know, you can take a look at the paper. They have a very comprehensive table for each month. January, some disease likely to happen. February, some disease likely to happen. It's very interesting. The newborns data can also have some disease risk, right? So I agree with the author is that during the individual's lifespan, from per womb to tomb, they have a lot of data, and the network have changed, and it's the dynamic network, and the metrics will change over times. And the second thing I think we should consider is a personalized multi-scale network. They have a lot of the wearable device, they have a lot of diagnosis, they have a lot of clinical lab tests and mobile device, and also they have a lot of network, right? And it's over the time, but it's also related to each patient. So how to do the personalized multi-scale network to model the dynamics of the complexity disease, it can be also a challenge. So this is a third challenge. At the end of talk, I just want to introduce the healthcare domain. Actually, right now is the big data industry now. And a lot of data generate. Per the lab time, they have 10% of data is the clinical factor, and it's 0.4 terabits. And for the genomic factor, it's more than 30%, and 16% is external factor, right? And right now, this is just the estimation right now. I think after 10 years, after 20 years, they have more and more data. The human beings have been generated. Maybe double this figure, maybe triple the figure, I don't know. But right now, they have a lot of data generated for each patient. For the healthcare domain, although people think have a lot of money, have a lot of paper opportunity, but I think the most exciting thing for me is we need to, this industry is to help people to live longer and feel better. This is the reason I'm interested in the healthcare domain and also the biomedicine domain. So it's very good industry, it's help the people. And very good, IBM realized this, and IBM think the commitment to health is IBM's moonshot. And someone was interested in why IBM interested in the healthcare domain, and where the data come from. We do have a lot of data. For example, we acquired the Exploris, which is the EMR data. We have 15 million EMR data. We have children data. We have 3 or 4 billion of the claims data. We have Merge, which have a lot of medical image data. Vital is the personal care management data. current, and also weather.com. We have the weather.com, then we have a lot of environmental data. And we do the cloud computing and cognitive computing. We have a lot of exciting things to do. At the end of this talk, I just want to introduce, I'm working in the Center for Computational Health, and we do a lot of analytics across the patient similarity, predictive modeling, disease modeling, and visualization, and the translational medicine, like what I introduced now. And we combine data-driven thing and knowledge-driven thing. And in my team, and we have about 10 people, and with very different background. Some people have the biomedicine background, some people is the medical doctor, and someone is the data mining machine learning guy. And we have multiple positions available, like intern, postdoc, engineer, and researcher. And please let me know if you have any question. And thank you. And I don't know how to explain this picture, and I think the matrix model can be used for a lot of industry, right? Not only for the healthcare, but it can be used for whatever industry. Since we have a hammer, we can find the application, and everything looks like now. Thank you.